The first presentation on convergence tests was deliberately geared towards getting to the ratio test as fast as possible so that we could talk about power series. This is the second presentation on convergence tests. It should not be understood as something that says, here's all the other convergence tests, because in fact that is not the case. But rather than saying that, this is a presentation that just talks about a few more commonly used convergence tests that can be used, for example, to figure out whether a Taylor series or a power series converges at the boundary of its interval of convergence, where it is not clear whether at those points the series converges or diverges. Let's take a look at what we have. So, for daily use, if you want to say it that way, the ratio test really is highly effective, and that is also something that we can see in the presentation on power series. But there are many series for which the ratio test does not work. And some of these series arise, for example, at the bounds of the interval of convergence of power series, and that means we need further convergence tests if we want to know more details about power series, for example, or about series that just come up from other contexts. Remember, however, that no one test will do it all. There is no single convergence test that says, and give me an arbitrary series, and here's when it converges, and here's when it diverges. And the other thing that I want you to remember is that common mistake, just because the terms go to 0 does not mean the series converges. So remember the harmonic series, the sum n equals 1 to infinity of 1 over n. That is a sum of terms that go to 0, but the sum itself is infinite. And in fact, that is a good reminder, because the alternating series test is one that is dangerously close to something like that, that talks about terms whose limit is 0. Namely, the alternating series test takes a sequence of numbers bk that are greater or equal than 0, whose limit is equal to 0, and so that the sequence of numbers is decreasing. So bk plus 1 is less than or equal than bk. I think formally that would be that we say non-increasing, but that's one of those words that I have a hard time wrapping my mind around. Then the alternating series, sum n equals 1 to infinity, negative 1 to the n plus 1 bn converges. So it's alternating because we're putting what is called alternating signs in there. And so that means it's dangerously close to saying limit 0 gives you convergence, but it only does that for the alternating series, not for a series of positive terms all the way through. And so yeah, series of this type are called alternating series. How can you prove something like that? Well, if you line up your number axis vertically, then your first summand will be just b1, and that's positive. And when you then go from the first partial sum to the second partial sum will be b1 minus b2. So your second partial sum will be going down. The third partial sum is b1 minus b2 plus b3, so you're going up again. The fourth partial sum goes down again, because now you've got b1 minus b2 plus b3 minus b4. And that just keeps on hopping like that, and because the bk's go to 0, the oscillations get smaller and smaller, so it stands to reason that this ultimately stabilizes at some limit. And we can actually prove that in a mathematically pretty watertight fashion, because we know that if we look at an even number term in this series and an odd number term in this series, and an even number term in this series, then the odd number term is positive, the even number term is negative, and their difference is greater or equal than 0 because the next term is less than or equal than the previous term. So that means the sequence of the even partial sums, the partial sums that go from 1 to 2n, that'll be a non-decreasing sequence, because this sequence can be parsed as b1 minus b2 plus b3 minus b4 plus b5 minus b6, and so on. Similarly, if I take an odd number term and subtract from it the previous even number term, right? So now I'm looking at b2n plus 3, which comes after b2n plus 2. Now we have that the odd number term here is the next one, so this one is smaller than that one, so this difference is less than or equal than 0. Because of that, we have that the sequence of the odd partial sums is non-increasing, because I will have that the first sum here will be b1, then I add to that b3 minus b2, to that I add b5 minus b4, and so on. So I add a bunch of negative terms now. If I pair them up in the right way, in pairing them up in such a way that I'm always pairing an even number term with the next odd number term. And that tells me that now, because the difference between the even numbered sum and the odd numbered partial sum is just the 2n plus first term, which is -1 to the 2n plus 1 times b sub 2n plus 1, that's going to be greater or equal than 0. We have that the odd numbered partial sums, which are non-increasing or going downwards, and are greater or equal than the even numbered partial sums, which are non-decreasing, so those are going up, which means that we've got a non-decreasing sequence that is bounded above by a non-increasing sequence, and so by the monotonic sequence theorem, the even and the odd partial sums converge because they are both monotonic and bounded. And because the difference of these two sums is b2n plus 1, which goes to 0 as n goes to infinity, the sequences of the even and odd partial sums have the same limit, and that means the overall sequence of the partial sums converges, and that means that the series converges. Okay, as challenging as the proof of the alternating series test is, as simple is its application, because if I want to show that the series sum n equals 2 to infinity -1 to the n divided by ln n converges, well, all I can say is, but of course it does, because 0 is less than or equal than 1 over ln n plus 1. I guess I should have said ln n here. Let me fix that real quick. Oh no, this is the next term. Okay, so 0 is less than 1 over ln n for any n, so in particular also for ln n plus 1. But 1 over ln n plus 1 is less than 1 over ln n, and that's because ln n plus 1 is greater than ln n. Remember that taking the reciprocal changes the inequality around. And so the other thing we know is that the limit as n goes to infinity of 1 over ln n is equal to 0, even though the logarithm goes very slowly to infinity, it ultimately does, and 1 over infinity is 0. And that means that this series satisfies the hypotheses of the alternating series test, namely the limit of the terms is equal to 0, and the terms are non-negative and non-increasing. So application of the alternating series test is fairly easy. It also then is a bit of a one-trick pony, because unless you have the -1 to the n or a -1 to the n plus 1 in your series, you'd be hard-pressed to apply the alternating series test. The limit comparison test has a bit wider applicability, and the limit comparison test says the following. If we have two series with positive terms, and if the limit of the quotient of the an over bn is equal to a number c that is greater than 0, then either both series converge or both series diverge. So both series have the same convergence behavior. Again, here is where this idea of mathematical reasoning certainly again enters the discussion that we have about series here, because we now have another test. We have another limit where we take a limit of terms, and it's not a limit of a sum, it's a limit of a quotient, but it's not a quotient of consecutive terms. And when that limit of that quotient is greater than 0, as opposed to in the ratio test being smaller than 1, then the series have the same convergence behavior. So again, we have to be sure that we train our mind mathematically to the point where we can keep all these things separate in our mind and apply them when appropriate. But other than that, the proof isn't too bad, because when the limit of the quotient is a constant that is greater than 0, then for sufficiently large n, we have that an is approximately equal to c times bn. And because only the terms with large n determine whether a series converge or diverge, converges or diverges. And because multiplication with a constant does not change the convergence behavior, both series have the same convergence behavior because basically the sums of their tail ends are just constant multiples of each other. In terms of applying the test, if we want to determine if the series sum n equals 1 to infinity 30n squared over 5n to the 4th minus 7 converges, we could use the comparison test, and in some ways then the limit comparison test is a bit of a simpler shortcut because it allows us to avoid working with inequalities in many cases. If I wanted to compare this series with anything, it would probably be something like n squared over n to the 4th, which is 1 over n squared, the sum of 1 over n squared. So if I form the quotient of 30n squared divided by 5n to the 4th minus 7 divided by 1 over n squared, well, if I take that limit, I just multiply with the reciprocal of 1 over n squared. I get the limit of 30n to the 4th divided by 5n to the 4th minus 7. We expand with 1 over n to the highest power of the denominator, so we expand with 1 over n to the 4th. We get the limit of 30 divided by 5 minus 7 over n to the 4th, which is 6, which is greater than 0. And therefore, because the sum n equals 1 to infinity 1 over n squared converges by the p-series test, the series sum n equals 1 to infinity 30n squared over 5n to the 4th minus 7 converges by the limit comparison test. And that's how we work with the limit comparison test. We're closing out with two theorems that talk about how to estimate remainder terms. Remember that when I started talking to you about convergence tests, I mentioned that it's actually not terribly common to actually be able to find the exact value of a series. But what we can always do is, because we know that the sum over the tail gets smaller as we make our ending index in our sum larger, one of the things that we can do is we can estimate how big the remainder is, which would then tell us how close our partial sums are to the overall value of the series. And so if we have a non-negative decreasing function f, and s is a series sum n equals 1 to infinity f of n that converges because of the integral test, well then the sum n equals n plus 1 to infinity f of n is less than or equal than the integral from n to infinity f of x dx, and that means that the difference between the value of the series and its capital N's partial sum here, is less than or equal than this integral, and this integral may be something that we can estimate or compute. If we want to prove this result, we just go back and think about how the integral test worked. Here is our function. The terms of the series are the evaluations at integer points, and then the series itself is the area of these rectangles underneath the function that are always having their top right corner at these blue points that are the evaluation of the term of the sequence. And so that means that if I take the difference between the total and say the sum up to 3, that would mean that I take the first 3 terms away, and that means that I have the terms starting at 4, 5, and so on, which is the sum of n going from n plus 1 to infinity f of n. And if I sum from 4 to infinity in the series, then I actually pick up this rectangle here, which means I also pick up something that has to be estimated by the integral starting at 3, which is why the sum n equals n plus 1 to infinity f of n is actually bounded by the integral of f of x starting at n. So that is the rough idea behind this estimate, and we can use that now to compute an approximation, for example, for the sum of the p-series sum n equals 1 to infinity 1 over n to the 5th with an error of less than 10 to the negative 4. Well, I would want to make sure that my sum n equals capital N plus 1 to infinity 1 over n to the 5th is less than or equal than the sum n than the integral n to infinity 1 over x to the 5th. And that is, if we take the antiderivative of x to the negative 5, that's negative 1/4 x to the negative 4, or negative 1 over 4x to the fourth. The integral will be the antiderivative at infinity and at n. Well, at infinity it's 0. At n I get 1 over 4 n to the fourth. And now I'm just going to make this upper bound less than or equal to 10 to the fourth, which means 1 over 4 n to the fourth should be less than or equal 1 over 10 to the fourth, which is the same as 4n to the fourth being greater or equal than 10 to the fourth, because when we go to reciprocals, the inequality has to be changed around. And that would mean that n to the fourth, or I take the fourth root first, so fourth root of 4 times n has to be greater or equal than 10, and the fourth root of 4 is the square root of 2, so n is greater or equal than 10 over square root of 2. 10 over square root of 2 is 5 times root 2. Root 2 is 1.4 something. 1.4 something times 5 is 7 point something, which means n greater or equal than 8 will do it. And so then the approximation would be the sum n equals 1 to 8, 1 over n to the fifth, which is something that can be worked out with a calculator, and it's approximately 1.03688, and that means here that these digits are completely accurate. This one, if you round it, would actually be a 9, and depending on how far we have suppressed the error, it could also be an 8 if it doesn't change too much in that fifth digit here. So that is then a pretty good approximation for the value of this p-series. If you need 4 digits, you definitely have enough in here. That leaves us with one more way to estimate remainder terms, and that actually goes back to alternating series. Namely, if I have this a-ins be a non-increasing sequence of non-negative numbers, and let the series sum n equals 1 to infinity, negative 1 to the n plus 1 a-n converge because of the alternating series test. Then the sum n equals n plus 1 to infinity, negative 1 to the n plus 1 times a-n, this remainder term, is less than or equal than a sub n plus 1, which means that the difference between the overall value of the series, which is the infinite sum, and the capital Nth partial sum is actually less than or equal than a sub capital N plus 1. How would that be proved? Well, I would take my summation here, and that summation, the absolute value of the summation, is just a(n plus 1 minus a(n plus 2 plus a(n plus 3 minus a(n plus 4, and so on, independent of whether I'm starting with an even or an odd index. I've got an absolute value here, so I have to make sure that my result is positive, and I can force that by simply realizing that the terms decrease or are non-increasing, which means this difference is non-negative, this difference is non-negative, and so on, and so on. If I bracket that differently, I get that this is a(n plus 1 minus a non-negative number minus another non-negative number minus another non-negative number. So I realize that this absolute value is less than or equal than a(n plus 1, because all I do is I keep subtracting, but I can't dip below 0 because I know that the result is non-negative. So that means that this is less than or equal than a(n plus 1, which is what we have claimed here. That means if I, for example, want to find the first 4 decimal places of the value of the alternating harmonic series, well, that would mean that I would need to take my remainder term, which is the remainder estimate is negative 1 to the n plus 1 divided by n absolute value. I make that less than or equal than 1 over 10 to the fourth. That would give me an error that at most affects the last digit in a plus minus 1 fashion. And that would mean that n is greater or equal than 10,000. And that would then mean that I would have to add the first 10,000 terms of this series. Well, that gives me that the actual first couple of decimal places are approximately 0.6930. 0.693 is close to accurate, right? It could drop down to 29, but basically then because the error could affect this digit and because those are so close, I just recorded a couple more digits, and that would be a pretty good estimate, an estimate within 10 to negative 4 of the value of the alternating harmonic series. And with that, we have some more uh, convergence tests for series, as well as some ways to actually estimate values of series should we choose to do so. You can already anticipate what the homework is going to be like. You're going to have some series for which you have to check whether they're convergent or divergent, and you're probably going to estimate some values. Have fun with that.